Example 4, minimizing time. A man launches his boat from point A on a bank of a straight river, which is 3 kilometers wide. And he wants to reach point B down here, 8 kilometers downstream on the opposite bank. So here's point A, and he wants to reach down here as quickly as possible. Now he could row his boat directly across the river to point C and then run to B. Or he could row directly to B. Or he could row to some point D, which is between C and B, and then run to B. Now, if he can row 6 kilometers per hour and run 8 kilometers per hour, where should he land to reach B as soon as possible? Now, we assume that the speed of the water is negligible compared with the speed at which the man rows. Okay, so there's a few things that we need to refer to here. First, we need to see that we're going to let x represent the distance between C and D. So we can see here that that represents the distance from C to D. Okay, and then the running distance is the absolute value of D to B. So therefore, if we want to find out the running distance, which would be here, okay, we don't know what that is, but we do know that that distance is going to be an absolute value because we know it has to be a positive number, right? And we know that from C to B it is 8 kilometers, but we need to subtract the x to find the distance of the absolute value of dB. Okay? And if we want to find the distance, okay, of A to D, okay, well, first and foremost, what do we know? Well, we know that this represents a right triangle. Okay, we know that this is 3 kilometers. We know that we have the x distance here, and we want to find the distance between A and D. Okay, so let's write down the given information so far. So we know that the distance from C to D is x. Okay, we know that the distance, or the absolute value of dB, is equal to 8 minus x. And so over here, let's find the absolute value of AD. So if we know that that is squared, the hypotenuse is going to equal x squared plus 3 squared. Okay, which gives us the absolute value of AD squared, which is equal to x squared plus 9. And if we take the square root of both sides, then we know the absolute value of AD is going to equal the square root of x squared plus 9. So that tells us that the absolute value of AD, or the distance of AD, is the square root of x squared plus 9. Okay, now we also need to know that since we're dealing with time, okay, we know that distance is equal to the rate times your time. And we also know that if we want to solve for time, well, time is equal to the distance divided by the rate. Okay? So we're looking for the distance, which is equal to, or time is equal to the distance divided by the rate. Okay? So what we're looking at now is we're looking at the rowing time and the running time. So we have the row time and the run time. Okay, well, recall that the row time represents the distance of AD divided by the rate from A to D. Well, what is the rate from A to D? Well, the distance of the row time is 6 kilometers. So that's going to be the rate for the row time. Okay? And we have the absolute value of dB, and that represents the runtime, and we can see that the rate for the runtime is 8. Okay, so what we want to do is we want to be able to find the time, which is t, and t is going to equal. So what we're going to do is we're going to add these two together, and that's going to give us our time. So in step 4, we're going to write this in terms as a function. So we know that this is going to be t of x, and we know the absolute value of AD is the square root of x squared plus 9 divided by 6, plus the absolute value of dB is going to equal 8 minus x, and that is divided by 8. Okay, so we're going to have to take a derivative of this function. So before we do that, let's just simplify this a little further. So we know that this is going to be 1 over 6. We know that the square root of x squared plus 9 can be written as x squared plus 9 to the 1/2. Okay, and this is the same thing as saying 1/8 and multiplying it by 8 minus x. So if we distribute the 1/8, we're going to get plus 1 minus 1/8 x. Okay, so now what we want to do is we want to take the derivative of this function. So taking the derivative of this function, we're going to get 1/2 times 1/6 times x squared plus 9 to the negative 1/2 times the derivative of what's inside, which is x squared, so that's going to be 2x. We know the derivative of 1 is going to be 0. And the derivative of negative 1/8 x is minus 1/8. Okay, so now let's go ahead and simplify as much as we possibly can. Okay, so we do know that when we multiply this 2 and that 1 over 2, it's going to give us 1. Okay, and then we know that we're going to have that x in the numerator. So therefore, t prime of x is going to equal so far x over 6 times x squared plus 9 to the negative 1/2 minus 1/8. And let's just write this where it is t prime of x, which we have x in the numerator, and it's going to be 6 times the square root of x squared plus 9 minus 1/8. Okay, so now that we have this derivative, what we want to do is we want to set this derivative equal to 0 so that we can find the critical number. So in order to do that, we're going to take x over 6 times the square root of x squared plus 9 minus 1/8 and set that equal to 0. Okay, now let's add 1/8 to both sides. So we have x over 6 times the square root of x squared plus 9, and that's equal to positive 1 over 8. And now let's go ahead. We can either multiply both sides by the LCD or we can use the cross product. So we're going to use the cross product. So we have 8 times x, which is 8x, and that's going to equal 6 times the square root of x squared plus 9. Okay, if we divide both sides by 2, we can simplify the 8 and the 6 to be 4x, which is equal to 3 times the square root of x squared plus 9. Okay, now what we want to do is we want to be able to eliminate that square root. So we're going to square both sides. We're going to square the 4x, and then we're going to square 3 times the square root of x squared plus 9. So this is going to give us 16x squared. And this is going to equal 9 times x squared plus 9. Let's distribute the 9, and we get 16x squared, which is equal to 9x squared plus 81. Now, if we subtract the 9x squared to both sides, then we're going to get 7x squared, which is equal to 81. And therefore, x squared is going to equal 81 over 7. Okay, so if we take the square root of both sides, then x is going to equal the square root of 81 over 7. Now, we're only using the positive value because we're dealing with the distance. So that's what we want. So x is going to equal approximately, the square root of 81 over 7 is 3.4. So now that we have our critical number, we need to go back to our original function, okay, which is the one in step 4 here. So let me go ahead and copy this function, okay, and I'm going to call this step 7. So in this function, okay, what is the domain of this function? Well, what are all the values that we can put in for x? Okay, we can put any value in for x into the square root of x squared plus 9 because you're going to square it. But over here to the right, okay, 8 minus 9 is going to give you a negative number. So the domain of this function, okay, and we only want positives, is only going to be between 0 and 8. So this only gives us 3 possibilities. So to see whether the minimum occurs at this critical number or at the endpoints of the domain of 0 and 8. So the following values of x that we can pick are 0, the critical number of 3.4, and the value of 8. So if we plug in t of 0 into the function, so we have the square root of 0 squared plus 9 over 6 plus 8 minus 0 over 8 gives us a time of 1.5. Okay, if we find t of 3.4, plugging that back into our original function, so we have 3.4 squared plus 9 over 6 plus 8 minus 3.4 over 8, well, that gives us approximately 1.33. And then if we want to find t of 8, which is the endpoint, then we have the square root of 8 squared plus 9 divided by 6 plus 8 minus 8 divided by 8 gives us approximately 1.42. So which one gives us the shortest time? Well, if you take a look here, the shortest time is when t is at 3.4, when x is 3.4 and the value of t is equal to 1.33. So therefore, we would say that the man should land the boat at a point approximately 3.4 kilometers downstream from his starting point.